Hello, my name is Calvin Carpenter, and today I will be deriving the finite differencing form of the heat diffusion equation. But before we can dive deep into that, we're going to have our assumptions for this scenario. Our first assumption is that heat is only going to diffuse, and in order to show that, we're going to take two terms out of the diffusion equation and set them to 0, or assume they're going to equal 0. We're going to take our second degree partial derivative of temperature over partial derivative y direction, partial derivative of temperature, second degree, but in the z direction. That's going to be 0. Second assumption is going to be that our heat generation scenario, or our last, is that our thermal diffusivity equals our thermal conductivity for our heat capacity times our density for that specific volume. So for this scenario, we're going to be working with a bar that is a finite length, and we're going to set this initial length at 0 and our final length at W. The temperature at this initial length, say length is going to be L. At this initial length, it's going to be set at 350 Kelvin. And then write that a little bit smaller. Can keep some room. Temperature at length 0 is going to be 350 Kelvin. And then for length W, our temperature is going to be 400 degrees Kelvin. Going back to our first assumption over here, we can make a statement based off of it. So since two of our dimensions of our heat diffusion equation are now set equal to 0, we can redefine it. So our change in temperature with respect to time is equal to a second degree partial derivative of temperature with respect to the x direction. Also, I forgot our thermal diffusivity constant out front there. So that's going to be the equation that we're going to be working with. So for both of these initial and final temperatures, we can make a generalization or where T is always going to be between 0 and infinity. Now that we have this kind of base coat laid down, we can state our initial conditions. So our initial conditions are going to be at any L value temperature is going to be equal to 300 degrees Kelvin at T equals 0, as long as L does not equal 0 and L does not equal W, because we've already stated that our initial temperatures are going to be 350 and 400 at the ends. So yeah. We can split, we're going to split this bar up into blocks here. And whenever I say at any L value, T equals 300K, I'm talking about any of these. At the initial time, T is equal to 300 Kelvin. I'm just going to describe real quick what all these values mean. So we're going to be working with temperature mainly, and so our L is obviously our position, and our N is our time. And so in terms of position, L is equal to an integer, which I'm going to say is F, times delta X, which is the distance between any one of these blocks. And so you're just going to assume that the temperature in all these blocks is uniform. So we can just measure the blocks as a whole. And then with time, N equals an integer, I'm just going to say G times delta T. So we can have like even time blocks between values. All right. So next, let's kind of expand this term a little further, so we can kind of get a grasp of what our equation is going to look like. So this term is going to expand out, and it's going to look like this. So we're going to have our partial differential in terms of x times our change in t over our change in x. And so this term basically means 1 over the change in the x direction. And this term is the more interesting one. So this one, I'm just going to rewrite it down here. This one's going to equal an average between two values. So we're going to have the temperature at a specific time, 1 block forward, minus the temperature at a specific time at the current block over delta x. And then the second value is going to be the temperature at the current block minus the temperature at the block previous. So I can kind of paint this picture for you. So the first term is comparing, say this is our L. We're comparing this block to this block, and then this block to this block. All right, so now we're going to bring down this equation, start working with that a little bit more. We're going to expand the left side. So our left side is going to expand into the temperature at a specific length in a future timestamp minus the temperature at a specific length in our current timestamp over delta T. It's going to equal our right side of the equation, which is our thermal diffusivity times, and then we're going to use our values down here, the values that we're going to calculate an average of. It's going to be temperature at a future block to the right at the current timestamp minus the temperature of the current block over the distance traveled. And then we're going to subtract our second scenario, which is, or the second, not scenario, the second block that's going to affect the current block, which is going to be the temperature of the current block, the block we're focusing on, minus the temperature of a block to the left over the distance traveled. And then all of this is going to be divided by delta x in order to get our average. So we're going to work through this a little bit further so we can simplify it a little bit. So first of all, we're going to move our delta t over and simplify our denominators over here. So our temperature, one timestamp in the future, minus our temperature at our current timestamp equals delta T times our thermal diffusivity. And then we can take these delta X values out since they're all common denominators, and we can put it out here as delta X squared. Sorry, I just realized you can't see that. It's delta X squared. And then what's left on the inside, we can just add our terms together. So it's going to be our temperature, one block to the right, minus 2 times our temperature of our current block, plus the temperature of the block to the left. So we're going to do two more things with this equation. So we're going to move our temperature at our current timestamp over to the other side since we already know that value, and we're going to be solving for the temperature of our current block at a future time. And we can also substitute something in for this. So we'll have our temperature at our current block in our current timestamp, and then the second value I highlighted in the equation can substitute for this. So R equals delta T times the thermal diffusivity over delta X squared. So we can substitute that in times our values. I'm just going to bring them down. So this is our final equation for the finite differencing form of the heat diffusion equation. And to kind of explain all of it, make it all make sense. So we want to find the temperature of our current block. Scroll back up. We want to find the temperature of our current block. Just erase this real quick. So say this is our current block. So T. This is what we have, and this is what we want. So we want it one timestamp in the future. And in order to find that, we need to know temperature of L minus 1 at n, at time n, and the temperature of L plus 1 at time n. And we only need to know these values because heat can only travel to our block at L from its neighbors. And so yeah, that's pretty much it for this step. Next, I'm going to go into Collaboratory and show you some graphs at how the heat diffuses through this bar and some other cool stuff like analyzing this equation. Now we're in, and we're go ahead and see if we can graph plot the what the heat like. First, we're going to be so we can find our plotly so we could plot okay. Now that we have our stuff that we need, we're going to go ahead and define a few variables. So nx, the number of sections of the bar. Find our number of steps. Our R value. Right? don't remember what R was, it's our heat activity change. All right. So now that we have our variables for our variables. So next we're just going to code in a simulation of a bar, of our bar. So we're going to set our initial and final temperatures. As you remember, it was 350 on the left end, and it was 400 on the right end. So T0. And that is on the left end. That's the right end. So the reason why I use -1 brackets is because -1 refers to like the last temperature in the bar, so it'll be like, so instead of saying like 1000, I would say -1. It'll just go back to the far right side. So now we're gonna import another function. This will basically import our array. So now we're gonna make our figure. Sorry. Do one row and one column. Now we're gonna add our scatter. Just gonna set x equal to our y value is going to equal our temperature. And connect all the lines. We're going to want to connect the values with lines, sorry. And then the name. Initial. Sorry, I need. Name's going to be initial. I think, yeah, this is wrong. All right. Okay, yeah, now that we have our plot figured out, I'm gonna set up our for loop. So for I in range So for every, so basically it's going to plot a point for every time step. From 1 to our 100,000 that we set. So every I in range of nt plus 1, we're going to put in our, so we have our t of 1 to -1 equal t of 1 to RT of timestamp ahead the end. There we go. Minus 2 minus 2 times t 1 to negative plus t -2. So that's our force statement. Then so if I equal our 100,000 sorry, no, I'm gonna make that equals 0. Then oh my god. Again, we're setting our x equals x t. So our temperature's on the y-axis. Mode. We're going to connect them with lines. And name, we just want it to be timestamp. So that should be the end of that. I figured out the problem. We just needed a hole in there. Show our figure, and we can see how the heat diffuses through the bar. So we can change a few things in order to make this a little better. So we can increase our number of variable with other. So let's go ahead and run this. Okay, I guess that didn't really change visually, but the heat does diffuse into the bar, increase the amount of time that it has diffused, but we can change the heat, the R value, so that it increases the heat diffusivity of the bar, which you can't really do that on can't really change the heat diffusivity of material, but for this case, we're just going to see what it looks like when something faster. Okay, that changed a little bit. Kind of coming off the either end a little bit more, but let's try increasing our, happens when we increase our value to 0.55. Okay, so as you can see here, whenever the R value, I guess we have a cap on our R value. So we're going to decrease the R a little bit and see if we can get a less wacky result. Okay. So as you can see, the graph is still pretty crazy whenever you put that R value in. So we have temperatures reaching 7.5 times 10 to the 18th, which is completely possible. So we're gonna, assuming our threshold is 0.5. Can I just do that real quick? Put it like 49999. So yeah, the graph stays normal whenever you increase the R value, but you can't go above 0.5. It's interesting. All right, so here we learned that we have a threshold for R. So that R value can't go above 0.5 or we'll get instability within the graph and accurate results. So in the next video, or in a video in the future, we are going to explore why that is. Thanks for watching.